Yes. Okay. So today I will present some work done in collaboration with Andrei Gritzun. This is a sort of has been the coronation, so to say, over 3-4 years long joint activity with him through a joint fellowship of the Royal Society and the Russian Foundation for Basic Research grant. So this is the goal of this work. The goal of this study together with Andrei has been to try to to look at atmospheric blocking events through a new lens. So what I will talk about is indeed the study of some features of the low frequency variability of the atmosphere in the mid latitudes. And we try to address 3 questions: whether the blockings are associated with anomalously unstable or stable conditions of the atmosphere, whether there is something special about the onset or decay phases of the blocking, and if there is in some deep sense something special about the blocking events. And at the end, we will get hopefully some interesting extra bonus result. So a lot of the work I'm going to talk about is contained in a publication that has come out just a couple of days ago with Michael. It's a paper on reviews of modern physics that's been published on July 31st with the title Physics of Climate Variability and Climate Change. And the main reference is the paper with the same title of this presentation that I published together with Andrei in Climate Dynamics earlier this year. And previous work that has been somehow the starting point for what I'm going to talk about is a previous investigation done together with my former PhD student Sebastian Schubert, and that was published in Quarterly Journal of the Royal Meteorological Society. So first thing is we're talking about climate, and climate is indeed a non-equilibrium statistical mechanical system, and the non-equilibrium comes from the presence of a non-homogeneous absorption of solar radiation. Solar radiation is preferentially absorbed near the surface rather than aloft, and near low latitudes, at low latitudes rather than at high latitudes. And the entirety of the processes of the climate are basically set off by this inhomogeneity. And the climate reaches an approximate steady state by a complex set of processes and feedbacks. And in particular, the large-scale energy transport of the atmosphere of the ocean tends to compensate the imbalance at the top of the atmosphere in the low versus mid to high latitudes. So the climate dynamics realizes itself in a very non-trivial fashion. That is, we have a variability on a vast range of spatial and temporal scales that cover more than 10 orders of magnitude in both directions. So when we study the climate, we more or less implicitly accept the fact that we are concentrating on a range of scales. So today, this has relevance also for modeling and relevance for data, for observational data reconstruction, sorry. Oops. And today we're going to concentrate on the synoptic and planetary scale variability. So when we talk about planetary scale variability of the atmosphere, this is the so-called domain of low frequency variability. So we are talking low with respect to the typical synoptic variability that has has time scales of few days. So here we are typically talking about weeks or more. And the phenomenology of the low frequency variability has been one of the main targets of investigation of dynamical meteorology since ever, basically. Some very classic investigations from the Scandinavian School of Meteorology are reported here. And the main feature that was observed was that the low frequency variability is associated with a breakdown of the typically zonal condition and a slowdown or even a breakdown of the jet. So in particular today, I'll talk about one of the most important phenomena associated with this low frequency variability, the so-called block. By block, the name of this word has to do with the block of the zonal jet. And these are seen on weather maps as a long-standing, persistent, and geographically almost stationary waves that appear as large deviation from the typically almost zonal conditions. And they have they are characterized by some sort of different qualitative features. In particular, here I'm showing you the omega block because the isolines of the geopotential resemble the letter omega, and another kind of block is the so-called diffluent or dipole block, because of course these isolines look like a dipole. But the phenomenology of the blocking events is very complex. So next, the blocking events take preferentially place either over the Atlantic, the mid to high latitudes of the Atlantic Ocean, or in the Pacific Ocean. So we talk about Euro-Atlantic or Pacific blockings, and sometimes they take place at the same time in both oceans. So we talk in this case about global blocking. So the first question is a global blocking just sort of a coincidental presence of these two blockings in the two sectors, or is there something special about being a global blocking? So, and an important aspect is the following. Usually, of course, the dynamics of the atmosphere is incredibly complex, and there are so many different factors. But indeed, see already a tank experiment, a rotating tank experiment, where a much simpler system is considered can exhibit the fundamental features of blocking events. So there's in particular the fact that for given boundary conditions and given value of the parameters of the system, there is coexistence of more than one, and now I'm using the word in a sort of loose sense, attractors. There are competing metastable states, in particular one that can be associated to blocking and one can be associated with the zonal flow. So this was a series of experiments run by the group of R.S. Sweeney together indeed with Michael, showing this. So there is something fundamental about blocking. Now, how to study this phenomenon which I repeat as a very complex and non-trivial phenomenology. So the starting point, the classical way to study blockings follows the following path. That is, one takes a sort of simplified equation of the atmosphere, in particular typically barotropic models, but also barotrinic models, and one tries to find two or more solutions, time-independent solution to the problem, and hopefully the idea is to try to find that for some parameters one can get more than one solution, and then the stability of such a solution have to do with the lifetime of the system. So now so one hopes to find a solution that looks like a zonal flow, and another solution that looks like a blocked flow. And so this is a sort of the root of the equations. There is another root. Another root is the sort of a most extreme level of coarse graining one can think. So one identifies, and this is a classical exercise of synoptic originally, so-called synoptic meteorology, one identifies the existence of different class of weather patterns that repeat approximately themselves in the course of the seasons and across years. And then one tries to study the probability of transition between these different weather patterns. And indeed, it's starting with the 90s, there's been a lot of effort in modeling this transition as just using finite state Markov chains. Now, the idea is this just something empirical, or is there something deeper about this? These methods have shown a very good skill, so we'll try to understand why they work in some sense. Why are blocking important? I mean, of course, you can have a fetish of weather maps and be interested in those, but there is something very relevant about blockings. First, because of their persistent condition, they can lead to extreme weather events of many kinds, heat waves, floods, and droughts. But there is another problem, is that these blocking events are extremely hard to forecast with numerical weather prediction system, including the most recent ones, and they are also hard to simulate with climate models, including the last generation of climate models. So these are objects that are hard to capture, both in terms of prediction and in terms of statistics. So what has been our take on this very classic problem? So we have chosen what is called a model of intermediate complexity. This is the Marshall-Montaigne 1993 just 3 layers quasi-geostrophic model that has proven huge skill in describing the dynamics of the atmosphere exactly in the scales of our interest. I will not go much into this model. I just want to say that this model is run in such a way that has a good representation of the typical winter conditions of the mid-latitudes and is in a sort of a strong turbulent regime. So we want to study the instability of this model, and you know, the sort of classic way to do this is through the formalism of Lyapunov exponents and of covariant Lyapunov vectors. Lyapunov exponents, in a nutshell, represent the rates of growth and of decay of the asymptotic rates of growth or decay of infinitesimally small perturbation with respect to a reference trajectory. And if a system has at least one positive Lyapunov exponent, well, the system is a good candidate for having chaos. These Lyapunov exponents are constructed as asymptotic properties and through the tangent linear. And an important, so we get a spectrum of Lyapunov exponents, the same number as the number of degrees of freedom of the system. Here, of course, I'm making a lot of mathematical assumptions about periodicity and so on, which I leave to the imagination of the person who is listening to me. And an important quantity is, I mean, we want to compute the spectrum of Lyapunov exponent, and let's say we have n, small n, positive Lyapunov exponents. This gives us the dimension of the unstable subspace. Now, we can construct a lot of important dynamical indicators with the Lyapunov exponents. In particular, what is really important is the size of the first Lyapunov exponents, the sum of the positive Lyapunov exponents that, according to the Pesin identity, gives us the Kolmogorov-Sinai entropy under suitable conditions, and the Kaplan-York dimension, which gives us the dimensionality of the attractor, which is typically, I mean, for dissipative system, smaller than the number of degrees of freedom. So now we do this. These are asymptotic properties, but sometimes we want to understand what happens in some regions of the phase space. So we can construct finite time local equivalents of all the quantities I've just discussed. So we define a time scale of reference, t, and then we study for each at each position in along our orbit. So in principle, everywhere in the attractor, the finite time Lyapunov exponents over a time scale t. That will be for us 1 day. And then locally, we can define finite time Lyapunov exponents and the local number of unstable directions. Now, this is the kind of spectrum we expect we get in our model. So we have about 500 degrees of freedom. We have 37 positive Lyapunov exponents. So the system is very turbulent. You get cyclones, you get blockings, of course, and many other things, and the Kaplan-York dimension of about 90. So this is a very highly turbulent system. These are the asymptotic results, but we want to see the fluctuations of the instabilities. So if we look at the daily fluctuations, we discover that this system is extreme, the attractor is extremely, and I repeat, extremely heterogeneous. The predictability varies a lot, and it depends enormously, is extremely state dependent. The number of local unstable dimensions fluctuates between 30 and 65, or even less, between 20 and 70. So different regions of the attractor, different regions of the atmosphere are extremely different in terms of predictability. Now, and you can look at the first Lyapunov exponents and as well as the Kolmogorov, the finite time estimate of Kolmogorov-Sinai entropy gives us a similar picture. What happens when a blocking takes place? Basically, what we discover is the following. First, during blockings, the atmosphere is on the average more unstable than typical conditions. Second, the longer the blocking, the more unstable is the atmosphere. Third, in the case of atmospheric blockings, the instability peaks at the onset and at the decay phase of the blocking. And we interpret this as a result of the fact that the blocking is in some sense an organized structure. So the system needs a lot of information to create this. So now the result is blockings are associated with higher than average instability of the atmosphere, even if weather prediction during the blocking is easier than in typical conditions because persistence is strong. Nonetheless, on the scales, what wins is the problem of constructing such organized structure. For the Pacific blockings, there are different features, but the main message is that also Pacific blockings are more unstable than typical conditions, and the longer the blocking, the higher the instability. Global blockings are more unstable than both. Okay, now let's go to the next slide. The result that blockings correspond to regions of low predictability as confirms other results obtained through a totally different approach by Faranda et al., who studied the recurrence of weather patterns in the actual atmospheric data using extreme value theory. So we have a good reasons to believe that somehow some of the typical view on the phenomenology of blocking is wrong. So in the previous work I did with Schubert, we also saw that blockings are associated with higher intensity of the Lorentz energy cycle. Now, last part of the presentation, we want to understand the nature, in some sense, of the blocking. So the way we do this is using the formalism of unstable periodic orbits. In a chaotic system, we know that the attractor is densely populated by unstable periodic orbit. And in principle, this describes the so-called skeletal dynamics of the system. They are extremely hard. They are not easy to capture, definitely not through numerical integrations. And because these are unstable closed solutions, but still there are methods to find them. Now, how likely is to find the closed unstable orbit when you have, say, 40 positive Lyapunov exponents? You know, a priori, this seems like an impossible task. Can we really do any reconstruction of an attractor of a very highly turbulent system in this way? And you know, one of the great advocates of these approaches has been since long time Predrag Cvitanovic, and who proposed this as a way to look up turbulence. I was very skeptical of this approach until, in fact, this study I did with Andrei. Because what we did is without using high performance computing or the fanciest of the methods, we found about 2,600 UPOs in this 500 dimensional space. They seem a lot. In fact, of course, this is a huge subsampling of the whole of UPOs. But still, this is a sufficient number to draw already some relevant conclusions. So the first thing is, in this set of 2,600 UPOs, these are, I repeat, exact solution to the dynamics, we get an incredible diversity of instability. So we have the first Lyapunov exponents ranges from slightly larger than 0 to very large. The Kolmogorov-Sinai entropy can vary by almost an order of magnitude, and the number of unstable directions in these UPOs is, again, extremely diverse. So now, what is this? This is the proof, in some sense, of the heterogeneity of the attractor of the system, which explains the heterogeneity of the tangent space we have described before using the finite time Lyapunov exponents. And in particular, the special interesting result is that blockings are associated with anomalously unstable periodic orbits. So when we are in a blocking, we are indeed close to a bunch of the most unstable among the unstable periodic orbits. So blockings in this sense are special. They overrepresent by an order of magnitude, by really a lot, the very unstable and very rare UPOs. So I repeat, blockings are rare. They are rare because they are very unstable. This is associated to the trace formulas, in fact. And these UPOs, so when you are in a blocked state, you are near a very unstable orbit, unstable periodic orbit. So these unstable periodic orbits somehow give some sort of ontology to blockings. Okay. Now, the bonus result is the following, is that the variability of the number of unstable dimensions that we have found by finding UPOs with different number of unstable dimensions is a very strong and serious violation of the hyperbolicity of the system. And this has a lot of fundamental consequences. First, it's for a system that has such a violation of hyperbolicity, it's very hard for any numerical model to shadow trajectories for very long. Second, a model like this does not have structural stability. So in some sense, it's extremely hard to construct to get the statistics right. And a model without structural stability does not obey anything, or hardly obeys anything that is like a linear response. So in that sense, we understand why it's extremely hard to predict how blockings will change with altered climate condition, which is another of the well-known problems. A finally interesting result is that if a model like this has a huge variability in the number of unstable directions, if we perform data assimilation, we cannot restrict ourselves to assimilating only on the stable manifold, which is one of the very important new methods, the methodologies that have been proposed in data assimilation, because we might, because of the attractor is very heterogeneous. So some regions of the phase space might have a larger number of unstable direction on a larger region. So concluding, we have combined the technology, the mathematical technology of Lyapunov exponents, finite time Lyapunov exponents, and somehow the opposite viewpoint on the dynamics, the one based on unstable periodic orbits. And somehow, hopefully, we have elucidated some of the interesting and complex aspects of blockings. And the nice thing is that blockings seem to be responsible for the presence of such, if you want, are the byproduct or are the manifestation of the heterogeneity of the atmosphere. So the atmosphere is extremely, if you want, non-axiom way, very non-hyperbolic, exactly because we see features. Otherwise, it will be more featureless than we find. Of course, to understand this in the real atmosphere, we would need to look at more complex model. But I have the feeling that the results here already give some good new input for our understanding of atmospheric blockings. Thank you very much. Yes.
Do we have time for a quick question?
I have a question, Valerio.
Yes.
Can I ask a question? It's Chris Jones.
Hi, Chris.
So, do you actually think that the unstable periodics orbits themselves, if you could isolate them, would have, if you looked at them as spatial solutions,
yes,
had the structure of a blocking
event?
event?
Yeah, absolutely. This is how we classified.
That's your idea?
Yeah. This is actually how you construct these sort of yes, these statistics here. So the black line is the statistics of all orbits, and then the blue and red lines correspond to the UPOs that have blocking events. So where you can detect blocking events, even persistent blocking events. Okay, so this is exactly what you get. So these UPOs, let's say 5% of the UPOs are exactly in a blocked state. So can be some correspond to Atlantic blocking, some correspond to Pacific blocking, and some correspond to perpetual global blockings. And these are the most unstable ones. That's actually the very interesting.
So a second question.
Yes.
So a follow-up question then is, could you calculate numerically the Floquet exponents of those unstable periodic orbits? And would they correspond?
Yes, we get all the spectrum of exponents. Yes, we could. And they are much more, so let's say that let's say if typically you have 40 unstable dimensions, in the case of the most unstable UPOs, you can have 60 unstable dimensions, many more. And these are very rare, of course, and this is explained exactly by the trace formula. And on the other side, they have a much larger Kolmogorov-Sinai entropy than the average. So they are very anomalous, very rare, and very unstable. In fact, this is coherent. but you see them.
Larry,
Right.
Yes.
effects of stochastic, introducing a stochastic term in this would be, but I notice we're already 4 minutes behind the schedule, if I understood the schedule right. So possibly I should email that to you.
Yes, briefly. Oh, sorry, there are some people waiting, and they will come in now. So I meet all. So welcome everyone. We are so the message is, of course, if you had stochastic perturbations, just very briefly, this can have a very strong impact on some of these orbits. So you can, adding a stochastic parametrization can enhance a lot some resonances. So you have to be careful. This is very important. This tells you that the system is sensitive to stochastic parametrizations, which is something that we know. So that's why it's not just adding a little bit of noise. Strange things can happen.
Mm-hmm.
This is actually pretty much in line with these results. Okay.
Cool.
Thank you.
Could I also throw in a
Yes.
This result for data assimilation? I mean, maybe not everybody in the audience is familiar with the fact that students and other collaborators emphasized data assimilation in the, I know that you know that, as being to be controlled, and you are now pointing out that, and I just wanted to mention that to generally that would encompass mixing between stable and unstable. Yes. David's question about noise. Noise is actually good for you.